Should I start? Okay. Good morning. So yesterday, during the lecture, we saw this general decomposition of the entropy production using conservation law. That was abstract, quite complicated, but during the exercise session, I showed you that in simple cases, there's actually a very way to understand how this works. But I hope that you appreciate nonetheless that there's a procedure to do it in cases where it's more complicated. And I showed you that chemistry is one example where quickly things get non-intuitive. And this kind of concludes the part where we focus on average stochastic thermodynamics. Of course, we define things at the level of single transition, but then I always averaged over the quantities to get ensemble average description. And this is where we derive this splitting of the second law. Now I'm going to briefly, I don't plan to go in too many details about that, but I want to show you, because this is actually something that played an important role in raising attention on the field of stochastic thermodynamics, is fluctuation theorems, is the fact that we can also define thermodynamic quantities along single stochastic trajectories and make statements about how these quantities fluctuate. Okay, so this is the part on fluctuating level. In reality, once we have the local detail balance, which is a property defined really at the edge level, we have all the ingredients there. It's only a matter of evaluating things along a trajectory. So we saw that W, the rate, is a transition probability per unit time. The master equation gives us how the probability distribution evolves in time. But we can also look at a single trajectory. So if we would have the state I as a function of time, like that, let's say time 0 is here. I start looking at my system here. My system will stay during a certain amount of time in this state. Then it will jump at this time. You can call it T1. And it will jump choosing a certain edge at T1. Then it will stay in another state until it jumps to another state at T2 via an edge, which is the edge at T2. Sorry? Time. Y. It's I of t. It's the state I. You remember I was using, so Wij was my rate matrix. So I was using I label for the index, for the node, for the state of the system. So this is the state of a system as a function of time. And then I can jump again until time, let's say tau. Okay, so T2, T3, and they might be, depending on the trajectory I look at, there might be many more transition or many less. Okay? So that's the picture of a trajectory. And we can actually evaluate the probability to follow such a trajectory. So I will denote symbolically a trajectory by psi. Okay, so this is one trajectory. So the way I will do this is, okay, I start with the probability that at time 0 I observe my state in I0. This is I0. Okay. Well, actually, this is I0. And then I need to sum the probability to stay. I need to take into account the probability to stay on that state before jumping again. And that probability to stay is related to the probability. You remember that, so Wij is the probability per unit time to jump from j to I. And we discussed this at the very beginning. The diagonal part of that matrix is the sum over j different than I of Wji. So this is the probability not to jump, because this is the probability to jump, so this is the probability not to jump. And so if along this trajectory I want to sum all the probabilities not to jump during those intervals, I can do it here, but then here, then here, then here. What I'm doing is basically integrating from 0 to t this diagonal probability, and the way to write it in terms of edge is always a little bit painful. I need to now put a delta here and I of t, so let's see why. Because this takes me the origin of the edge, and yeah, I is the origin of the edge. Where is my sum? I need a sum, right? Yes, I forgot the sum in my notes. I have a sum over E. Because I need to sum, I am on a given edge, and I need to sum over all the exit rates, which is this. Yes, so this is correct. Okay? So in short, what I'm doing here is, so for this one, it would be e to the minus, no, it's already minus, W I0 I0 over the time interval T1. Here it would be e to the W. Yeah. So this would be e to the minus is already here, so I don't need to put it. The W I0 I0 to stay during a time T1. And if I do this one, I would have, and since it's it might be time dependent, I'm integrating over it from 0 to T1. And so here it's time dependent. You cannot read this? Okay. Let's put as an example. So let's say that this is state 1, okay? We have, how many states did I draw here? 4. So this is state 1, this is state 2, this is state 3, and this one is 4. So the probability to stay on state 1 during a time T1. This will be e to the W11, and I need to integrate this because it's time dependent from 0 to T1. So this is, this is a dummy integration variable, okay? Because the rate is time dependent. Now, the next one is the probability to stay from T1 to T2, W to 2 dt. etc. I do this here for 3, for 4, okay? And I can put everything together, you know, then I'm clumping together the integral, and I get this. Here I simply wrote it as the sum because of this, right? The diagonal part is minus the sum over the exit rates. And this is what I write here. Okay? But what I didn't count yet is the probability to have jumps at the different points. Okay? So now I need to add this. This will be a product over the k jump along my trajectory of jumping at time tk. Okay? Now let's consider, I could have chosen a better example to take a time reverse. Let's consider the time reverse trajectory, meaning, rather than drawing it because it's going to be ugly, I'm going to simply show it in the backward. Now I'm imagining I'm considering time reverse trajectory, I will denote it psi bar, to go in this direction. Okay? So if you allow me to erase this, because it's going to be convenient to have. Yes? What is the? The origin of the edge and the value of the state at time t, this I of t. So the probability now along a time reverse trajectory, and I should say that for the time dependent case, I will also assume that I time revert my rates. So if I have a certain time dependent over this time scale, imagine that my rates, of course, each of them will have a different one, but there's a given time dependence in my rates. When I go backward, I also take the time reverse time dependence in the rates. Okay, I will have the probability of the final state of the trajectory, I of tau, because now I start in this state here. The probability to stay is going to be the same, because as I said, I time reverse the rate. So the probability to stay that long in this direction or that long in this direction with time-dependent rate is going to be the same. And the jumps, they now happen in the opposite direction because it happened like this in the forward, it happens like that in the backward. So this is going to be minus E T K. And the key point is this fact, is the fact that the waiting time drop if I take the ratio. So the ratio is what we're going to define as the entropy production along a trajectory chi. It's the log of the probability to go via a certain path forward in time divided by going along the time reverse time. And I put a wiggle here. The wiggle is to say that my rates have the time reversed driving. If I have a time-dependent driving, I need to specify that when I look at the probability during this backward process, it's evaluated with the time reversed driving, time-dependent driving. Okay, so if I take this ratio, this log ratio, what happens, as I said, this drops. I'm left with the log of the initial and final condition, and a sum of logs of ratio of the different jumps. So I sum over all jumps, the rate forward divided by the rate forward at tk. And I have the initial and final condition, log p I of tau, I should not write too small, at time tau plus log pi 0 at time 0. Okay? And something that, because I think later on I will also use that form, let me just note that since this is the change between here and here, right? So I also express that change, because that's a state function, as the sum of the changes here, plus here, plus here, plus here, plus here, plus, I accumulate the changes. And as a result, I can take in to my sum to have something that is more reminiscent of what we had for the entropy production. But now I take in the probability to be on the origin of the edge at time t1, so that will be the edge. Yeah, it's a bit small. I need to write this bigger. So the probability to be on an edge, on the edge here at time tk. I will not specify. I will not write it because it becomes heavy. But it's tk, so it's the edge at time tk. At time tk, probability origin of minus the edge at time tk. And since I took these changes, which are those changes in, I need to also add the other changes. This will be the sum minus the integral over d tau 0 to t of the derivative of the log of p of I of t. That is a function of, if I integrate over, this is tau, this is t, and this is t. Okay? So this is now, I'm integrating the changes of log p along states I. So these are those contributions. This one, this one, this one, this one. So you see that if I sum this one, this one, this one, this one, plus this one, this one, this one, then I get this minus this. Yes?
What does P of chi function represent?
So this is the probability to observe this stochastic trajectory. Because we started with the Markov jump process. We started by, I started by defining the master equation, describing how the probability jumps in terms of those rates. But the underlying dynamics of such a master equation is a Poisson Markov jump process, Poisson condition on the state where you are. And so you can see this master equation as resulting from an average over an ensemble of trajectories, and that's what defines the probability, and we looked at how this probability evolves. But you can also look at it for a single realization of the process, and then assign a probability to the full trajectory. And this is what we do here. We say, okay, what is the probability to observe such a trajectory? Actually, you can, this is why I'm saying, there are systematic ways to do it with more rigorous tools. This is more, a bit more hand-wavy. But you can really show that if you sum over all these trajectories, you recover, and you ensemble average over them, you recover the master equation. You can actually decompose. It's a kind of path integral representation of the master equation. Okay? Now the point is, if I ensemble average this is actually the entropy production. And therefore, so the ensemble average of sigma, let me first note this, that the ensemble average of sigma is a relative entropy, because you remember the relative entropy definition, now it's at the trajectory level. For any probability distribution, the definition of P prime is the sum over I pi log pi over pi prime, and this is always greater or equal to 0. So now we have that the expectation value of the entropy production defined along a trajectory is always positive, okay, reassuring. But one can also convince oneself that the time derivative of that thing is really what we called this, which was also positive at the ensemble average level. Okay? Now, more importantly, I mean, it's good to see that at the average level things are positive. It also gives a nice interpretation which is consistent with what we have at the ensemble average level. You remember you asked me what is the meaning of the entropy production, and we discussed that it's measuring this asymmetry along every edge. This is the same spirit. What is the entropy production? It measures the time reversal asymmetry between observing certain trajectory forward in time versus observing the same trajectory backward in time. So it has the same flavor of a metric measuring statistical asymmetry under time reversal. Now, we have more than that because we can also, and this is a trivial consequence of the definition, this is called an integral fluctuation theorem. We can simply, if I average now, I mean, this formally, this is very sloppy. It's a sum over all trajectory. But I think it's sufficient to get the idea. So I'm simply putting here the definition of the entropy production along the trajectories. So what is this object? This goes away with this. It becomes a sum over all the backward trajectories, and this must be equal to 1. Okay? Yep.
Those top two equations we have written for an ensemble.
Yeah.
But actually they are true for each set of series of transitions also, right? I mean, the entropy production will always be positive even for one particular series of transition, right? I'm sorry.
No, I mean, entropy production along a trajectory doesn't need to be positive. So that quantity here, and this is going to be precisely the point of fluctuation theorem, there are realizations that give rise to negative quantities like that. And we will actually this is the whole point of fluctuation theorem. It's to show that actually the probability for negative events of that object is exponentially rare. But it can be negative. Yeah. Yeah, that's actually my next thing. So it's the positivity requires ensemble average. Yeah, that's exactly what so I simply write it here so that I can erase this. Here I use the fact that the summing over all trajectory, since the set of forward trajectory is the same as the set of backward trajectory by definition, this is why I can do this. This sum here is equal to 1 because I can replace this sum by, it's the same thing as summing over xi bar. Okay, now let's look precisely at what I was saying. Let's ask, what is the probability to have this object taking a certain value sigma? So this is, I sum over every trajectory. I put a delta to say I want all the trajectory, all the entropy production along trajectory that take the value sigma, P sigma. And now let me play with this. So the first thing I do is I sum over chi. Here I don't change anything. I replace this by P wiggle psi bar exponential of sigma along psi. Because of the delta, this gives me an e to the sigma that I can get out of the summation. And now, let me do it step by step. Now I replace this by this because by definition, if entropy production is an what's the name? Asymmetric under switch from chi to minus chi, right? It's obvious because if I switch this, I switch this. So sigma is, if I replace psi by psi bar, I get the minus sign. And so that gives me a plus. And then I have e to the sigma sum over I can of course replace this. This is equivalent to minus minus, and so this is equivalent. I could write minus minus, okay, sigma minus delta minus sigma minus. And now I use the fact that summing over all the set of forward trajectory is the same as summing over all the set of backward trajectory. And this is now the definition of P of minus sigma. And so this is the friction theorem saying that the probability to observe value of the entropy production that is sigma, so positive, versus the probability of observing minus sigma is actually given by an exponential. So this quantity can be negative, but it is exponentially rare. And that implies if you average, you can recover both the integral fluctuation theorem and using Jensen inequality, the positivity of the average.
Why did you use sigma plus small sigma plus capital sigma over inside the delta?
Why did I do what?
Why did you make that on sigma plus capital sigma under below the underline?
Here?
Just yes.
Because I changed chi to minus chi. Yeah, you see there's a bar here. Okay, so the first Now, when I proved this, there was this key assumption that I used. So this is actually going back to your question. To say that this is minus this. And actually, I should not have erased the definition of the entropy production, probably. There's a bit of caution here, because you remember that when I wrote it explicitly, the entropy production along a trajectory, we had the sum of the logs of the forward and backward rates at all the different times. And that part has this involution property. It's involution. But we had also the boundary term, which was log the final state plus log of the initial one. Okay, and this was the crucial step here. So if I want this to be a real identity, I actually need to make sure that the probability, you see, let's look at the trajectory like this. The probability here is the same as the probability here. Otherwise, this boundary term is a problem for the involution. Okay? So how can you make sure of that? There are two cases. One is steady state, because if I'm in a steady state, P steady state does not depend on time, right? So my P here will be the same as the P here. Of course, it's going to be evaluated on a different state, right? But the value of the probability distribution, well, the vector probability distribution will be the same. Okay? So strictly speaking, this is true at steady state. And there's another case. Yeah, so let's say this is okay at steady state. Say okay, 1 at steady state. And 2, there's another way to make this work, is the following. I need to start from an equilibrium. And now I will use what we learned about the decomposition of the entropy production. Let me assume that I start in an equilibrium state. Let me first write maybe the expression explicitly for the entropy production so that I can discuss this better. So entropy production can be decomposed in terms of the force. Yeah. So this is what we did yesterday, right? But now I think we need to integrate this. IF times F. So plus the partial derivative of phi along I of t, and the boundary term that is phi at I of tau plus log of the probability I of tau plus phi, no, small phi of I log p I 0. And this is the tau 1, this is the 0, 1. Okay, so we had seen this decomposition. We did it at the level of the log of the ratio of the rates. So it's obvious that we can do the same decomposition along the trajectory, okay? Now, we also saw that at equilibrium, this object, you see, pi at equilibrium, we saw is e to the minus phi I minus the big phi ek. This is actually it's the thermodynamic potential that comes from the log of the partition function. Okay, because I normalize, this gives me the partition function. Log of the partition function is log of the partition function is the potential, so I can immediately replace the normalization factor by this. Okay? This means that if I can argue that initially and finally my probability distribution is an equilibrium one, you see when I take the log of this, I get down the phi, and I cancel this phi. And these two terms will only become, again, if I can argue that I end and I start at equilibrium, this is going to become with a plus phi ek at time tau, and this one will become phi ek at time 0. And this is not a fluctuating quantity, this is a number. So I eliminate the problem of the involution because it came from the boundary term, right? So if I make sure that I start and I end at equilibrium, I'm fine with the involution. So I'm in the okay part for the fluctuation theorem. But now I need to imagine how I can do that. One way is imagine that you start, you remember, how do we get equilibrium? We put the forces to 0. So the system is at equilibrium. And okay, at time 0, we can turn everything on. You know, F non-zero. Let's go. We go away from equilibrium. And then at some point here, I stop driving. So F here is along the path, it's different from 0. I stop driving, and I let my system relax. I could also, here I can have time-dependent driving. So this guy is activated, this guy is activated. But here I stop. I turn off F, and I also stop driving. Stop time-dependent driving. And so I know that my system, it will take a certain amount of time, but will go to a new equilibrium. It doesn't need to be the same as this one, because since I'm driving, the value of the parameter can be different. So I can put a prime here. And also, I could turn off another set of, no. Yeah, it can be different because of the driving. So I turn off the driving, the force, and I stop driving, so this relaxes. Now, the key point I want to make is the following. During this relaxation step, this is 0 because F is 0. This is 0 because I stopped driving. Okay? So the only thing that is changing is these guys. These guys fluctuate while I'm relaxing, but eventually we reach equilibrium. So it means that I can write now a fluctuation theorem for, let me for short denote this by the work in a kind of, it can be, you know, first it doesn't have the dimension of work because it would need an entropy. But let me use work to make also the analogy with the Jarzynski relation, although this is more general because we have many different baths, etc. But let me call this W for short. So here W changes. This is the point I was making, but here W is 0. This means that my fluctuation theorem now that I can write for all this, so sigma is all this. Okay, so my fluctuation theorem for sigma now holds, but for sigma, as long as I start from here and end from here. But because I argued with you that W stops fluctuating here, it is 0, and that my final state is going to be a scalar. So this means that my fluctuation theorem now reduces to this. Okay? Do you agree with that? It's subtle, huh? But the old trick, I'm using the entropy production from here to here. And now involution is okay, so this holds. But I'm arguing that because I'm doing this trick of imagining that I turn off the force, and I show you, okay, W stops contributing here, so this entire part doesn't change anymore. So my statistics for W here is the same as my statistic for W here. So basically, the statistics of sigma expressed in terms of W is this. Delta phi is not a fluctuating quantity, so I don't need to write delta phi here. And I get this. And this in the simplest case where there are no forces and where I'm only driving the energy, so the phi is the free energy. This is the famous Crookes relation that many of you may have heard, where it's going to be the work if I multiply by the inverse temperature here. And notice also that this result at the end does not depend on this on this conceptual trick that I used, right? Because it was only a trick to make the connection between sigma that I expressed in terms of W. So in reality, as I can stop anywhere, and this will be true. I don't need to wait that my system actually relaxes to equilibrium. Okay? From this, by integrating, you bring this on the other side and you integrate, you also immediately get the analog of the Jarzynski relation. Okay? But again, this is more than the Jasinski relation. It's a generalization because it holds. The Jasinski relation was only considering this piece here. In the special case where the only thing that you drive is the energy. So the only thing that was time dependent are the energies of the states. Here you can drive the chemical potential, temperature, internal entropy, and furthermore, and more importantly, I would say, you can have non-conservative forces turned on. Okay? Jasinski and Crookes, in their original work, they consider detailed balance systems, systems where when you stop driving, you relax to equilibrium. This is true also in complete generality. Okay, now I have 15 minutes left, right? So just this I will not prove, but I can tell you that one can prove integral fluctuation theorem for the adiabatic and the non-adiabatic entropy production that we introduced. That's the first point. And the second point is simply to show you two historical experiments which played an important role to verify. Okay, the way I drew this is a bit ugly because number 2 was this, and steady state is this. So I want to illustrate, and steady state, of course, I don't drive, so I remove the wiggle. So these are the two cases where I convince you that the involution is not a problem. And now I will give you one example for each where experiments were done. I would like to keep, let me erase here. So first, this is, I think, historically really what popularized the field. Jasinski and Crookes did this early work. Jasinski 97, Crookes 99, and then a few more. But in 2002, the group of Bustamante in Berkeley they verified the Jasinski relation, and in 2005, so this is a science paper, and this is a Nature paper. They verified, so this is the Jasinski, and this is the Crookes. They verified in experiments where they were basically, this is an RNA hairpin. And they attach it on one side on the wall. On the other side, they have an optical tweezer. And they can control the force with which they pull on the RNA. So they're really opening the RNA. So you should imagine that this thing is going to do something over time. It starts like this, and then it starts partially opening. So it's like this, right? You have a few bonds still here, but those ones start to open, and then eventually it completely opens. And then they measure the work. And in the second one, which is the one I'm going to show you now, of course, I'm going to do a drawing. So this is W. They plotted P wiggle in the backward. They re-zip, and they also measure the work there. So this is P of minus the work that they plot. And here they plot P of W. And at the meeting point, they found delta F equilibrium. And they did this for different zipping speeds, so the probability distribution changed. You see that if this is equal to this point is the point where this is equal to this. So when this is equal to this is equal to this. So that's why this is the point where you get the change in free energy. And they could compare what they were, this point, this crossing point that they got from the experiments with data about the difference in free energy between the zipped and the unzipped form of the molecule. And it matched. So this really played a very important, I mean, you know, it's always, people start paying attention when there are experiments. So this really raised a lot of attention to the field. And the second experiment, so this is the case 2, an example of the case 2. Again, detailed balance system here. There's only one bath, so that's a special case of 2. And now let me give you an example of 1, which is the steady state fluctuation theorem. This one was in the group of Ira Maya. Science 2006. And Gossard PRL 2006. So what we have here is a system with a quantum dot, and the chemical potential here, I should put dots. There's a difference between the two sides of delta mu. And so they could, this also was an experimental challenge at the time. I mean, these two, because, you know, these were the first experiments who were really starting to look at single fluctuating event. I mean, here you need to measure the work of a single molecule, so it's technical achievement. And here they were to monitoring a single electron transfer. These are the first experiments in full counting statistics. The way they do this is they have another circuit on top where you pass a much higher current, and then you monitor, this current is coupled. So if you want, there's another current going on here with a much higher flux, and you monitor that current over time. So you get something that does a jump. Whenever an electron comes in, it affects the value of that current. And so from monitoring that current, you can deduce the statistics of the jump in this system. And in this context, the fluctuation theorem is for current or integrated current. And it's that the probability to observe n versus the probability to observe minus n is E beta delta mu times n. Of course, these things, you know, the bigger the bias, the more unlikely backward event will be. So this is also a challenge experimentally. It's very hard to test these fluctuation theorems when the bias compared to KT becomes large, because the statistics for the backward process becomes very, very bad. But these are the two contexts where these results were obtained. you have questions? Yeah? For this one to affect this one? Yeah. But you want this guy to affect this one in the sense that you want to monitor, this is the current, the measured current I as a function of time, right? So this is time.
For that to happen, the mainstream can't be too overpowering over, like it can't be like electrons to like.
Well, no, actually you want many orders of magnitude more electrons here because you want to have a flux that is actually not too fluctuating. Otherwise, you're going to have a lot of fluctuations here, a lot of fluctuations here.
So how did they eliminate the possibility that it was just some randomness or some random noise or just electrons bumping into each other? I can imagine a bunch of possibilities, like instead of getting an electron out, it could have been like electrons colliding and something going wrong in the system itself that the measurement changed.
This is a capacitive coupling. So physically, I mean, my drawing is crappy, and in any case, these drawings are usually symbolic. The way it looks like, okay, this is still a symbolic drawing, but there are no electron transfers like this. So how does it look? There are drawings in those papers of the actual lithographic system, but it is that part. Yeah, I fear that I'm going to do, it's something like this. So this is the dot, these are the electrodes. But the upper part, I don't remember exactly how it looks like. But there's no transfer of electron between this and the current that goes through that. It is a capacitive coupling. It's simply the fact that these electrons feel, because electron interact with electron, they feel the presence of these electrons. If there's an electron inside, there's a certain interaction energy, and so the value of the current takes a certain value. And if there's no electron, then it takes another value. Not a collision process. There's no. They do not speak to each other by collision. They only speak to each other capacitively. No, actually you can show that from this, because there's one thing I forgot to say, remind me to say. From this you can actually construct the cumulant generating function associated to n. And by expanding the cumulant generating function in the bias, you can show that at lowest order you recover fluctuation dissipation, but you also have all the higher orders in delta mu. And actually people use this to get beyond fluctuation dissipation relationships between nonlinear coefficients. Gaspar did that, and Nazarov did that around 2000. And this was already, this is in this context, but it was already early on understood by Galavotti that this fluctuation theorem actually, you recover close to equilibrium fluctuation dissipation, but that you can actually get nonlinear response relations because they hold arbitrarily far from equilibrium. They are I mean, it gets harder and harder to measure them and verify them, but the theory shows you can get delta mu as big as And what I forgot to say is that here there's a long time limit involved because there's an exact fluctuation theorem for sigma, but since this sigma contains both the electron current, but there's also the boundary term that fluctuates. And so to get rid of this contribution from the boundary term, you need a long time limit. So in these experiments, they also looked at how it, as a function of time, it converges to that. And for the history, there were also non-trivial effects because since these two systems are coupled, there's the real bias acting on this system is not only this, it is also to some extent this. And so you can do the theory by taking these effects into account and showing that they more or less explain what is going on. So there were small discrepancy and at the beginning, and it took some time to sort them out. Yes?
In the above experiment, how roughly is measured? Is it 8
I didn't understand.
In the optical trap experiment,
Yeah?
how roughly is measured?
Because they can monitor the deviation of the particle from the center of the trap.
It is just 8 times dx, right?
Yeah. Also there are complications. And it also took some time to deal with them. So, of course, I'm giving you the zero order version. But yeah. Because this FDX is not, you know, the definition of work here is in terms of the derivative of the energy. So I put this under the carpet. Okay, so this ends the part on the basics of stochastic thermodynamics. And tomorrow we will start with systems that can have a macroscopic limit. Good. Ah, really? Ah, that's good. I know, because I asked if I had 15 minutes, and you said yes. Ah, okay, no. Okay. Good. Then I can start the macroscopic part. Okay. Macroscopic stochastic thermodynamics. Okay, so now the idea is similar, but we're going to start describing the system in terms of occupations. So we have an occupation vector that consists of occupations of systems in different states. And I have n of such states. So imagine could be a molecule with n equal 4 state. And this describes the number of molecules in a given state. Okay? So my goal will be, I will first give you the very basic to make the connection with what I said, the stochastic term I said before. And then I will start showing you some example before we come back and start working on the theory again, so that we get a bit of a sense of what kind of systems we are talking about. But the simplest picture I can maybe already, yeah, you can, I think for chemistry you can see that 1, 2, 3, n are labels of species, okay? And then it's how many molecules of type 1, how many molecules of type 2, how many molecules of type 3 do I have in my systems. For a POTS model, it's going to be, you know, let's take actually the Curie-Weiss model that was discussed yesterday. We have 2 states, so every unit, every system can be in 2 states, and we care about how many units are in state 1 and how many units are in state 2. So in that case, big N would be 2, but we have a collection of units, and we care about how many of them are in a given state. So we go from, the key point now is that you will see this is stochastic thermodynamics applied to any system that can be described by an occupation vector. And so now we need to describe transitions between these occupation vectors. So n, there will be transition, will be transformed into n bar plus, I will use this. You will see in many instances it is the incidence matrix. For chemistry, it's going to be the stoichiometric matrix. But this is a vector that tells me, okay, again, n1, nn. I go to n1 plus delta rho 1 and n plus delta rho n. Okay? And of course, for a given rho, so rho is the analog of the mechanism that we had, the edges that we had before. It's going to typically be associated to a reservoir triggering the transition or a chemical reaction triggering, triggering a chemical reaction. Or electron transfers between one conductor and another one, okay? So typically, this vector is not full. It's going to involve only a few of them. It will be useful to go to the example. I do it really very shortly. And yes, so the property of this matrix is that if I invert the direction of the process, I get minus delta. And I write now the master equation for the probability of the occupation, okay? Because now I describe everything in terms of occupation. So this is going to be the sum of the rho, R rho, n plus delta rho, P n plus delta rho. So these are all vectors. Of course, these are functions of t. minus R rho n P n T. Yeah. Okay. Like this. And I can also rewrite this. This is the minus one. I can also rewrite this as R rho n minus delta minus rho. No, wait, what did I do? Yeah, so if I go from here to here, this is when I leave n. So this is the rate for leaving n. If I come back from n, I'm starting from this and I'm going backward. Yes, this is correct. And what I think here, what did I do? Yeah, it's also correct. It's that I can switch rho to minus rho, and therefore I can write this. So this is, for this term, I switch rho to minus rho. As a result, I got a minus sign here.
And sorry, what is R?
Is the rate. So what used to be our W along an edge is now the rate with which we jump in this direction via a mechanism rho. And the local detail balance, I will use this symbol for short to not have to write every time the log. So I define this kind of entropy production along the edge, rho, as the log of the rate like this. Okay, so this is exactly our log of W along the forward edge divided by W along the backward edge. And because of all the things that we've done and seen, we know that there's always, using conservation law, a way to write this as phi n minus plus delta rho plus phi n. So that's the change in free energy plus the non-conservative work that I write A rho, which you remember was IF times F. So that guy, we had it written as X rho times the non-conservative forces. So this was the YF. So this dot product is a sum over all non-conservative forces multiplying the flux of a given conserved quantity, which for short I will write A rho. Non-conservative, NC. So that's the part of the transition that I cannot write as a difference of potential. This is why it's called non-conservative. And we can easily see that the property minus rho of n plus delta rho, because we will use this, we are adding delta rho here. So this is going to be minus sigma rho n. I have this, my sigma and my sums, they always look alike. So these are sigmas, these are not sums. Okay? So this you can check that if you add this and you switch the sign, so this would be, you switch the sign, so this is minus rho, and then you add delta rho, so the delta cancel, and here you add the rho, so this is antisymmetric. And A rho is also, this I should have said, A rho, this is a consequence of the fact of this x here. A rho is also antisymmetric. A rho is equal to minus A rho. So with this, you find this. So this is a consequence of x rho being equal to minus x minus rho. Okay? And yeah, I think I will stop here and go to the examples. Now, obviously, I could go on and simply, now we have the two key ingredients that were our starting point for stochastic thermodynamics, right? The master equation and the local detail balance. The connection with the log of the ratio and the physics and the master equation, and so we can go on, do the different splitting of the entropy production, fluctuation theorems also for this. So you see the direct connection between the two approaches. It's just that instead of describing things in terms of jumps between edges and having property associated to nodes and edges, we move to a description in terms of occupation. Okay. Let's start with the Potts model, maybe, because that's a simple one. So examples, I will show three classes: the Potts, the chemistry, and the electronics. So here it's Potts because I can have an arbitrary number of states. I don't claim actually this to be the most general formulation, but this is the class of model that we've been looking at. So I have a unit, so this I call a unit, that has Q states, and I label those states from 0 to Q minus 1, okay? So our vector n is going to be how many units are in state 1, how many units are in state 2, 0, 1, and Q minus 1. And we have in total n units. So I will draw a few of them. I put dots because I could have other, So let me allow to do this kind of symbolically. And they feel each other when they are in the same state. Etc. Okay? So n of those units. And so let's say this unit is here, this unit is here. This unit is here. And this unit is here in this state. So what I'm saying is that only the units in the same state are going to feel each other. And they're going to feel each other with an attractive interaction, J over N. Okay, so units like to be in the same state. And so we have an attractive interaction that is proportional to how many units are in the same state. So for this system, we can write the energy, given what I said. It is actually a generalization to Q state of what was explained yesterday for the Curie Weiss, which has two states, where every unit has two states. So, yeah, let's start with the energy. The energy of these n units is, it's a mean field model, so because we take into account everybody interacts with everybody in the sense that every unit in one state interacts with every other unit in one state. We need to divide the interaction by the total number of units to make it intensive. And then we sum from I 0 to Q minus Y of J and I minus 1 divided by 2. These are all the pairs of units that are in the same state. Okay, so this is the number of pairs. J is the interaction between one pair. So this is the interaction of all the pairs. And it's attractive, so we have a minus sign. And we make it intensive by dividing by n. Now the entropy of this system is what I was alluding to already before, is the complexion number, because you see that if I'm defining this system by how many units are in state 0, I'm not specifying unit 1 is in state 0, unit 6 is in state 0, unit 15 is in state 0. I'm just saying there are 20 units in state 0s. So I lost information, right? There are many possible microscopic configurations that correspond to my level of description in terms of occupation. And this complexion number in this case is going to be, so n units, n factorial divided by n0 factorial, n1 factorial, nq minus 1 factorial. These are all the possible arrangements of microscopic states. Think of the microscopic state as really the list specifying where every unit in a labeled way, unit 1 is in this state, unit 2 is in this state. While if I look at occupation, I lost this information about who's in which state. I only know that there are a given amount of people in one state. And so the number of possible microscopic state corresponding to a given occupation is given by that. So we have the entropy of a state and the energy of a state. And here, the vector n, is mapped into n plus delta I. I will denote plus 1 minus 1 because my assumption is that you can think of it in the following way. You can imagine that there's a little arrow indicating in which state the unit is. And the transition will only be between neighboring states. Okay, so I can go from here to here, or from here to here. So these are the transitions that are going to happen at the level of a single unit. So this is why this delta matrix will be defined in the following way. Delta I will give you an example to make it more intuitive. J I plus minus 1 minus delta Ji, and this is all modulo the number Q, which is the number of state. So let's do it, for instance, for a 3-state unit. So if we had 0, 1, 2, now this index I, which is the analog of rho, labels the transition. So this is the I equals to 0 transition. This is the I equal 1. This is the I equal 2 transition. So the label is the same as the label of the origin. I orient it like that, the origin of the transition. And so if I write delta in this case, you can do it like this. By applying this I leave you to check it. But you can also do it directly intuitively. So in both cases, we have 0, 1, 2. So think of this as the index I, this as the index J. So the transition 0 leaves state 0 and goes into state 1. So this is transition 0 leaves state 0 and enters state 1 and doesn't affect state 2. Transition 1 leaves state 1, does not affect 0. So I said leaves state 1 and enters state 2. Transition 2 leaves state 2 and enters state 0. Voila. Now you can check that this formula matches with this. Okay, and this translates the fact that, as I said, you can imagine your little arrow. We only do transitions like that. I should also say that this is plus, because this is in that orientation. I leave you also to check the -1, the backward transition. This is simply this one. So you leave 1, you enter 0, and so just so that you have it. Okay. And since we have an energy and a free and an entropy, the potential will be a free energy, which is going to be E of n minus inverse beta times S E n. And my local detail balance so the log of the rate plus minus, this is I n divided by the rate of I plus minus 1 minus plus n plus delta I plus minus. This is going to be minus beta free energy in n plus delta I plus minus F in n. And note that something that I didn't say yet, but that is going to be crucial, because this is, should have named it, this is a non-equilibrium Potts model. what makes it, because at the moment it would be equilibrium in the, a detail balanced system. So what I do now is I impose a force, a clockwise force, so that every transition is biased towards this direction by a force F. So that force acts in this direction. Okay? So now, here, I will get plus minus F. Because when plus is when I go clockwise, I work against the force. When I go anti-clockwise, I'm going with the force. Okay, and oh. Do I take 3 more minutes or? Okay, my point, maybe I don't need to. I just want to tell you that I can show you, I can give you the explicit form for Arrhenius rates and for Glauber rates, and even a generalized Arrhenius which can be parameterized to be more general, and show you that they all satisfy this. So there's a class of rates that are traditionally used that do satisfy that, and furthermore, you can generalize, so you can specify a very large class of rates that satisfy this and use this to study this model. I just want to give you the references for this. Or maybe this I can give you next time. I will start by giving you the references there are various papers where we studied that. First with Herpisch, my PhD student, and more recently with Jan Maibohm. So we have various work on that. And it's a very rich model. Maybe on the last lecture I will show some slides with the study of this model. Just to give you a hint, the 3-state unit was the first that we studied. It's very interesting because you can have synchronization in this model. So at 0 force, it's a standard Potts model, which can have a phase transition from having all state equally populated at high temperature. And if you lower the temperature, it's going to be in one of the 3 states. So you have three fixed points, and that's the equilibrium transition to go from 1/3 probability occupation, 1/3 for each state at high temperature to occupation either in one of the 3 states. But if you add the force, you can have the emergence of an oscillating regime where there's a trade-off between temperature and force, and the unit starts aligning with each other, and they all start collectively rotating in the same way. And so that's yeah, it's a mean field Potts model. But non-equilibrium, that's the novelty. And that's why it gives rise to these non-equilibrium phase transitions. When F is non-zero, you can have a phase diagram that is like this. So if you plot, this is F, and this is beta J, and this is Fj, F over J. And you have, so this is the symmetric fixed point. So this would be the state in the 3-state unit, the one where every occupation is equal to 1/3. And here you have the multi-stable phase. So you have 3 fixed points. So you have multi-stability. And here you have oscillations. So you see it emerges at when you turn on F. And you can study this with, obviously the general theory I'm going to give you comes from the specific models that we've studied, and then we formulated the general theory. Constant. Yeah. In this model, f is the same on every node. Yeah. Okay. So we continue tomorrow.
Okay, so just to remind everyone, we need 2:30 again. There's an introduction session for like everyone, students will introduce themselves.
At 2:30.
2:30.